All right, so this one is over estimating square roots. And yesterday we talked about how to evaluate square roots, like square root of 1, which would just be 1, square root of 36, which is 6, and 100, because that's 10. And those are all perfect squares. But then remember we got the one that was square root of 6. And we're like, well, how are we going to do that? Because there's no number times a number that is going to give you 6 that is the same number. Same thing with 11, 79, and 120. We estimate the values of these square roots between their whole number counterparts. For example, square root of 11. That's pretty close. 11 is pretty close to 9. Why do I use 9? Because I know 9 is 3. It's on the other side of that, the closest whole number is 16. Why 16? Because the square root of 16 is 4. So it's going to be between 3 and 4. It's actually going to be a little bit closer to this one because 11 is closer to 9 than it is to 16. So when I plot this on the number line, I'm going to plot square root of 3, or sorry, square root of 11 closer to 3. Let's try another one. Square root of 79. First off, what pops in my head is 81. And 81, the square root of that is 9. That is pretty close to that one, so I'm probably going to be plotting it there. Now, 8 is the whole number that's right next to it, and the square root of 64 is 8. So definitely, 79 is closer to 81 than it is to 64. So I'm going to go to the number line at the number 9, and I'm going to plot 79 super close to it. 120. Well, the square root of 120 is really close to the square root of 121. And the square root of 121 is 11. On the other side, it would be the square root of 100, so I would definitely plot it closer to that one. So here's 11, and I'm going to plot it really close to 11, but it's got to be between 10 and 11. So that's going to be the square root of 120. So we're going to place these on the number line as well. Square root of 5 is pretty close to square root of 4, which I know is 2. On the other side of that would be square root of 9. It's definitely not as close to that. So I'm going to plot it between 2 and 3, between these two numbers, but I'm definitely going to plot it closer to 2. Square root of 17 is really close to square root of 16, which is 4. Square root of 25 would be on the other side, so I'm plotting it between 4 and 5, but I'm definitely plotting it closer to 4. 0.3 is actually between 0 and 1, but it's definitely closer to 0. Square root of 0 is 0, and the square root of 1 is 1. So I'm going to plot that really close to 0. Square root of 39, that's pretty close to square root of 144, which is 12. On the other side, it would be square root of 121, which is 11. So it's going to be between 11 and 12, but 139 is actually closer to 144. So I'm going to plot it closer to 12. 70 is going to be close to square root of 64, and close to, square root of 64 is 8, so on the other side would be 9, and that is 81. So 70 is 11 away from 81, but it's only 6 away from 64. So I'm going to plot that in between the 8 and the 9, but a little bit closer to the 8. Oops, put the wrong number there. That should have been square root of 70. So again, you're just looking for numbers that you do know to kind of figure out where it should be. At least you can narrow it down to where it's between two whole numbers. The next one says if the area of a square garden is approximately 239 square feet, what is the maximum whole number side length possible? So when we look at this, again, we're looking for a number times a number that gives us this. So we can work backwards and say the square root of 239 should give us our answer. But that one's not an easy one. So we need to figure out what's around it. I know that the square root of 256 is 16. So that means 15 would be over here because we're always going to be between two consecutive numbers, and that's 225. Now, it did say what is the maximum whole number length side length possible. So the area is here. Could we have 16? No, because that requires more area than what we have. So the maximum side length possible would be 15 feet by 15 feet. Now again, that means that the whole area for the garden will not be used, but this is just if we wanted whole number side lengths for our garden. So we're going to lay down some mulch in our flower bed. A bag of mulch covers about 60 square feet. So again, we're talking about area being 60. What is the maximum whole number side length possible for the flower bed to be completely covered? So we're looking for a number times a number that gets us to 60. Okay, well I know that 64 is on this side, so this is 8, which means that has to be 7, and 49. Now, 60 is definitely way closer to 64. However, if I had an 8 by 8 garden, I'd have 64 square feet. Do I have enough to cover that? No. So the maximum that I can use is 7 feet by 7 feet. So a 7-foot garden by a 7-foot garden would only be 49 square feet, and I have 60 square feet worth of mulch. So yes, I'd have enough, and there would be a little bit of leftover. The bottom of the square baking pan has an area of 67 square inches. What is the approximate length of one side of the pan? So we have the square root of 67, which is going to give us square root of 64 on one side. That's 8, which means 9 has to be on the other side, and that one's 81. So it does say what is the approximate side length of the pan, so which one are we closer to? In this case, it's not like that maximum thing that we were looking at. It just wants to know about how big is the pan. So 67 is closer to 64, which means we have about an 8-inch by 8-inch pan. So please complete the rest of the assignment in your workbook.